If you call Q the charge of under the flavor symmetry of your fields, essentially what you are computing is the following. The exponential of e to the I uf, if you call it y, you see that these guys get a contribution of the type y to the q. So from where G is essentially the number of BPS states, so annihilated by Q and Q bar, counted with sign of charge Q. So essentially you take all the states in your theory, you label them according to the charge, and you define this generating function that whose coefficients count the number of states that have a particular charge Q. And these are just only the BPS states of your theory. In particular, you see something that we saw in the explicit expression. This function here is holomorphic in Y. Okay? This follows from supersymmetry. There is no Y bar in this sum. So this operator interpretation, it's will be useful for black hole because immediately give a notion of states. What I will be computing later essentially is the number of BPS states of my black hole weighted by the charge that they have under the flavor symmetry. So this was the first observation. The second one, oops. Second one is, both are technical. First had a little bit of conceptual side more. The second one is purely technical, but just let me mention that everything I did for S2 can be replaced, the S2 can be replaced by any Riemann surface. And what you have to do is the following. With respect to yesterday, you have to substitute the one-loop chiral contribution, one-loop contribution for the chiral with that you remember probably is a rational function. You need to change a little bit this rational function. Yesterday there was here minus their charge plus 1. When you have Eiger genus, you put a G minus 1, hard phi minus 1. So just change the exponent. The vector are similarly changed. Instead of the R measure, you get some power of it. And the power is the power 1 minus j. And here, yesterday I put the measure. So these are the two things that you have to do in the integrand. Remember that the integrand is always a classical part times a one loop. And the one loop is the product of these ingredients for the matter field and vector field in your theory. And the other thing that you have to do, because when you have a Riemann surface, you have, unfortunately, you have extra fermionic zero modes that you have to take into account. So you have to change also the integrand in an ugly way, but luckily enough at the end the result is simple, and schematically, I don't want to give you all the coefficients as correct, but just to have an idea of what you should do. Essentially, you need to take the guy itself that you construct as yesterday. You take a second derivative with respect to the gauge variable and with respect to the magnetic variable, and you take a determinant over the Cartan variables, and you put everything to the power g. Later on, for the black hole, I will discuss the most general case, which is sigma, a Riemann surface of genus G. So I will use this formula. These are technically more involved, but at the end of the story, they don't bring much of a difference. Indeed, in gravity, if you look at the entropy of black hole with different horizons, you find exactly a formula which is always the same. There are a factor of G in front. Last comment is the following. Maybe yesterday you remember that in the explicit example, super QED, in order to deal with the magnetic flux, I resum them. I use the geometric series to resum them. And at the end, if you look back to your notes, I wrote an expression for the partition function that was something like that. This guy was not in the game yesterday because for U1 the Weil group is 1, but can be easily introduced in more general situation. What you can always do is something like that. So resum the magnetic fluxes, get the denominator, evaluate the residue at the denominator, and the denominator essentially, so yesterday what we did was to resum the geometric series until we got something of this form, a denominator schematically of the form 1 minus some function. I decided to call it e to the IB yesterday, and the residue theorem tells you that here essentially up to signs, so let me put a tilde, you need to take a determinant, and yesterday was just U1, so you don't see the determinant in the computation that I did yesterday, but this is generalization. At the denominator, you just get a determinant of this guy because you take the residue at a simple pole. It's just complex analysis. So this you can always do for all the models that I will consider in this talk. And when you have eigengenus, the generalization is simple. When you have eigengenus, is same. So sorry, and this is evaluated at the zeros of x e to the I b is equal to 1. So that's the logic. The poles sit at the position x star, and you evaluate the residue at this position. What you have to do when you have eigengenus is the following. In this formula, you see the picture is very simple. You add an extra power of g at the denominator. And what is interesting is the following observation that was made by Closet, Kim, and Willett a couple of weeks ago, that the situation is even more general. So if instead of having a direct product of S1 times a Riemann surface, you take a fibration, so essentially you take a cipher manifold with Chern number 1, Chern number P, so you take a non-trivial fibration of S1 over sigma G. The only thing that you have to do, you can use the same formalism actually, this is very nice. So if this is a fibration, the same formula is corrected in the following way. I'm not giving you the details, but now there is an extra object that you can insert inside that is constructed with the same ingredients. I will not give you the explicit form, but there is a quantity, T of u, that you can insert here, that you can put at power p, and the insertion essentially, and this sum is done again over all the solution of this equation, and the result gives you the partition function on a generic fibration. What is nice about this generalization is that even S3 sit here. Clearly S3 is the Hopf fibration over the two spheres. So with the same formalism, you can also reproduce the partition function on S3. This is the observation by these gentlemen. And I have no time to discuss the physical meaning of this condition, but it's actually interesting. So if you want, in observation 1, I was roughly thinking of, I have a three-dimensional theory, I take the compact part as 2, I make a dimensional reduction, I get some quantum mechanics. That's nice. It's the right picture that I want to use for the black holes. I get the Witten index of a quantum mechanic is a complicated one. I need to evaluate, count the ground states. This is a way of seeing it. The other way is to, instead of reducing on S2, you can reduce on S1. So you go from 3 dimensions to 2 dimensions. And it turns out that when you reduce it on S1, essentially by one loop effect, you can write an effective Lagrangian Hamiltonian for the gauge modes, integrating out the massive fields. And the result is that you get a twisted superpotential. And this twisted superpotential is such that B is precisely the derivative of this guy. This twisted superpotential has been studied in details by Nekrasov and Shatasvili in their business of integrability for gauge theories in 2 dimensions. So there is a close connection also with that topic. And it comes from dimensional reduction on S1. You can find all the details in this nice paper. Okay, so end of the comments, technical comments about the expression that I gave you yesterday, and here the third lecture really starts. Okay, the third lecture is about black holes. So let's introduce the other side of the story. So black holes. Actually, this will be ADS black holes, asymptotically ADS black hole. Well, I think all of you knows about the concept, well, the Hawking story and the concept that the black hole, the law of that rules the horizon of a black hole, the black hole itself, are very similar to the law of statistical mechanics. So you can attribute temperature to the black hole. This is usually computed in terms of the surface gravity. And you can also, and important for us, you can also attribute an entropy to the black hole. And most likely all of you have seen this formula in natural units without h bar, where you essentially take the area of the horizon, you divide it by 4, that's the Newton constant, and you get the entropy of your black hole. Now, I want to consider supersymmetric black hole. So in supersymmetric black hole are extremal and have a temperature which is 0. So from now on, we'll be working at 0 temperature, but still we have a non-zero entropy because the area of the horizon is different from 0. So obviously, this, well, both in the 0 and non-zero temperature case, this calls for an explanation. Where do we find the microstates of the black hole? You also know, well, I recalled yesterday that for asymptotically flat black hole, the string explanation for a class of them, a large class of them, was given 20 years ago by Strominger and Waffa, and it works in this way. So typically you study black hole that can be realized by putting together the brains. The brains intersects, the typical configuration is usually a D1, D5 system where there is an intersection of dimension 2. You compactify a circle in this dimension 2 word volume, you put some momentum on it, which is one of the charge of your black hole. And essentially, if you look at the gravity, you get black holes. And the entropy of the black hole is matched with a computation of ground states of the gauge theory, which becomes a conformal field theory in this two-dimensional intersection with a momentum along one dimension. And the way in which you do this is using tools of conformal field theory. So typically you use the Cardy formula that tells you how many states there are with a particular momentum along the circle. The Cardy formula enumerates the number of states in the conformal field theory with a given value of L naught, typically. And using the Cardy formula, you can find a nice explanation for the entropy of these black holes. Now, as I was mentioning yesterday, things are slightly different for ADS black hole. If you look at the full black hole, not only the horizon part, since the object is asymptotic to anti-de Sitter, and if you assume that every theory in anti-de Sitter has a dual, which is a conformal field theory in one dimension less, the natural place where to look for the entropy is now the dual conformal field theory. And now it's not a conformal field theory of dimension 2, which in the original example capture the horizon of the black hole, but if you want is a conformal field theory living at the boundary of the black hole itself. Now I will write you a metric and discuss this in detail. I will tell you a story about ADS4. I will comment about ADS5 later on. I have not much to say about ADS5. I don't know how actually today how to compute with this method the entropy for black hole in ADS5. This I will comment at the end. But ADS4 works quite well for a big class of big class of black hole. So the object that I have in mind as a metric, so it's a four-dimensional object, as a metric in four dimension of this form. So there is a radial coordinate r, there is a time coordinate t, there is a Riemann surface. I want to take a black hole that has an horizon which in general is a Riemann surface. The Riemann surface can be S2, is probably the nicest black hole, but there are also black holes with funny horizon which are Riemann surface, and they exist. So let's look also to these strange beasts. And I'm taking a class of black hole which is static. So you see there is no rotation term in this metric, and up to now I have written nothing because this is the most general static metric that fit the requirement that I want, because I put two arbitrary functions of r. Clearly one of them can be, you could put a third one, but you can always make a redefinition of coordinates in order to get it away. So this is the most general object that you can write. And to fix the notation that I will be using later on, you need to specify what is the size of this Riemann surface. I will be using notation where the scalar curvature of this metric, the two-dimensional piece, is 2 times, let me call it kappa. Kappa is a number that is frequently used in the black hole business. Is 1 for the sphere, 0 for the torus, and -1 for a Riemann surface of genus greater than 1. The logic why all the genus greater than 1 are identified in this way is very simple. You can actually write a metric. The metric that you have to write is of 3 types. You take S2, T2, and then you take an hyperboloid, a non-compact one. Then it's known that all the genus surface of a genus greater than 1 can be obtained by taking a discrete quotient of the hyperboloid. That's the reason why they all fit in a single class. So by taking quotient of H2, you get all the Riemann surface that you want. So I fixed the curvature of these guys to be essentially 2 or 0 up to signs. The other things that I want is that asymptotically this is anti de Sitter. So let's take a large R to correspond to the boundary of the space. And what I want is that this function has a behavior such that the metric becomes of this form. It develops a double pole. A double pole plus correction, obviously. This is true also only for large R. So the double pole signal that you have a space which is asymptotically ADS, and with a boundary metric which is not flat, but is time times a Riemann surface. The other requirement, I want also supersymmetric black holes, extremal black hole. The other requirement is that there is a particular value of the radial coordinate where the horizon is sitting, where this function here develops as the exponential as a double zero, such that you can write the metric in this way. Up to constants that I'm not putting correctly, so each of the terms that I'm writing can be multiplied by an arbitrary constant. I want a metric that has this schematic form. So it's easy to get this by requiring that this guy has a double pole. And if you tune the function v, you can also get a situation where these two guys cancel and you get a constant. So now the horizon is given as a direct product of sigma g times another spacetime, which is, however, a copy of ADS2. So the horizon of supersymmetric black hole, of static supersymmetric black hole, is ADS2 times sigma g. Sigma g is the surface of the horizon, but there is a throat, ADS2 throat that it's generated near the horizon. So these are general features of extremal black hole with zero temperature. I'm not committing to anything in particular for the moment. And solution of this form arise in general relativity if you have Maxwell-Einstein-Lagrangian. So what you need to have in mind is that you have a bunch of vector fields in the bulk, maybe also scalar fields and other things. But certainly you have gravity and vector fields. And indeed, in general, the example that I am going to discuss are the ionic black hole. The ionic black hole have electric and magnetic charge under this gauge field, and so they will be classified by certain numbers. The magnetic charge of the black hole you can obtain by integrating the curvature of one of these guys, or all of them. Typically, you will have many vectors, and you will have a different charge for each of them. And again, in the normalization I'll be using, I will call it this guy up to a factor of the volume of sigma g, I will call it P. And it will satisfy a suitable quantization condition. This is very similar to what I did yesterday. I'm integrating a curvature over a two-dimensional surface. This should be an integer in some appropriate unit. And this is the magnetic charge. I will call it P. This is the standard name in the black hole literature. I also want electric charges. Electric charges you can roughly do in the following way. You do a similar, let me write the index in such a way that supergravity people don't complain. I'll explain you why one is up and one is down in 5 minutes. Essentially, here I have to integrate something else. The electric charge I can integrate on the same Riemann surface
instead of F, it's dual. So the logic is that G roughly is the star of F. This is the electric charge. It's not really the star of F in general because the Lagrangian is a mess. So what is actually this guy is, this can be defined as 8 pi Gn times the derivative of the Lagrangian with respect to F. Essentially star F. Okay? So P and Q are the electric and magnetic charge of the black hole. In particular, in the particular case of S2, so the Riemann surface can be S2, this means that A lambda is something familiar, is just a monopole. If you in the gauge curve, the gauge potential is just minus P lambda cos theta d phi. The integral gives you the volume of the sphere times P. So you see this guy is the same that I use in field theory. It's not, this is there for a reason. For a Riemann surface, you need to write a more complicated gauge potential such that the integral is given in, is non-zero and integer. So supersymmetry. Supersymmetric black hole have been found almost 10 years ago, of this kind has been found almost 10 years ago. The first example was found by Cacciatori and Clem in 2009, 2008. And they have been found in gauge supergravity. Since there is a nice mechanism for determining the entropy of black hole when you work with a gauge supergravity, which is called the attractor mechanism, let me spend 10 minutes telling you some few basic details of this so that I can write this general formula for the entropy. So this is a supergravity. Is gauge, so typically it's one of the supergravity that you get as an effective action when you have an anti-de Sitter 4 times S7 or anti-de Sitter 5 times S5 compactification. When you compactify on the sphere and you get anti-de Sitter, typically you are getting a gauge supergravity. And the bosonic field content is the following. There is certainly a graviton. There are typically NV plus 1 vectors and NV complex scalars. There is one more vector with respect to the number of scalars because one of the vector, let me call it 0, sits in the graviton multiplet, while the other vectors, NV, combine with the scalar, let me call the scalar Zi, to make a vector multiplet. So there is one more vector, and V is just the number of vector multiplet in your theory. And it's useful to introduce an index, lambda, which runs over the NV plus 1 vectors of the theory. So the first component is 0, the other is an integer that runs over the vector multiplet. And the important point is that there is a general construction of this kind of Lagrangian that can be written in terms of homogeneous coordinates. So instead of using Zi, you can introduce a bunch of complex scalar fields labeled by lambda. So there is one more with the idea that these are homogeneous coordinates. Roughly, if you want, you can identify in some gauge, but it's not the only one, the physical scalars as the quotient of xi divided x naught. And the reason why this is useful is that the full Lagrangian is then specified in terms of a single object, which is a is called the prepotential. Is a homogeneous and holomorphic function of the X. And I'm not giving a tutorial on engaged supergravity, but let me write some terms in the Lagrangian just to understand what's going on. Clearly there is the curvature term, then there will be a kinetic term for the scalar fields, and already the metric of on the scalar fields can be can be derived by a Kähler potential, and the Kähler potential can be written precisely in terms of this function and the scalar fields in this way. So you take essentially derivative of this guy. These are always often written in this way with a simplified notation, the F lambda. And you make this combination, you take the log, you get a Kähler potential, you compute the metric that you put it here. Then, similarly, the kinetic term for the gauge fields is again constructed in terms of a function n, which again is written completely in terms of this guy, not writing you the full expression, but is essentially a second derivative of f plus corrections. So the same function controls the scalar fields and the vector fields. And here there are other terms, theta angles. There is a potential for the scalar fields. And again, the potential of the scalar fields can be written in a unique way using a particular combination of all these variables. So it can be written using this particular combination. I'm not writing all the details of how the potential is constructed, but it's something of this form. And in the potential, when you just have vector fields, is the only place where you can play a little bit with parameters. There is a set of parameters here. That's the only things that matters for defining the Lagrangian coupled to vectors, that are called electric and magnetic gaugings, sometimes are called electric and magnetic phi Heliopoulos. And essentially what they do is the following. The magnetic one is something exotic. It will not enter in our computation. And in most of the cases, it's typically zero. So don't matter about the second one. And the first one, the electric gauging, is essentially will be telling you the coefficient that enter in the superpotential. In particular, will tell you if there is an anti-de Sitter vacuum, what is the radius of anti-de Sitter. So it will fix the value of the cosmological constant. So if there is just one of those guys, it's just the cosmological constant for the model. There is no other things in the game. The interesting story about supersymmetric black hole is the following. Okay, so let me keep a few things about the general structure of the black hole. So gauge supergravity is a particular case of Einstein-Maxwell, so I can find solution of this type, and then I may ask whether they are supersymmetric or not. So supersymmetry requires few constraints on the charges of the black hole. There is a first constraint, which is the following.
the coefficients disgauging that enters in the supergravity Lagrangian and the charges are required to satisfy this condition, where K is written on the right of the blackboard. Or let me tell you that the full Lagrangian that I wrote before is actually covariant under a group of essentially electric magnetic dualities, that the group is SP to NV plus 2, and this is the reason why there are this index. Everything can be written in a way which is covariant under this group. Under this group, for example, G lambda and G lambda, P lambda and Q lambda transform as vectors, so that this combination is a particular invariant of SP. Everything can be written in a covariant way under the group SP. For practical purposes, what's the meaning of this condition? For practical purposes, these guys are the magnetic gaugings, are usually 0, so forget about them. You can introduce, but it's not important. So essentially, this condition is a condition on the magnetic charges. And this condition on the magnetic charges become clear if you look schematically at the variation of the gravitino. In order to make the black hole supersymmetric, you need to set to 0 essentially a covariant derivative, and again, up to signs and other things, the crucial point is that, sorry, here there is a particular combination that I want to write, is, sorry, this way, E mu lambda plus other things. Okay, so the gauge field enters in the variation of the gravitino, and they enters in this particular combination. Now the point is that I'm turning on a background for the magnetic field, which is exactly the background that I turned on yesterday. So this background, so this guys is essentially P lambda cos theta d phi on S2, or more generally is a connection on the Riemann surface. You see that there is a P appear here, the magnetic charge. So the constraint here, G times P equal 1, essentially, is the one that tells you that you have to cancel the spin connection. The spin connection on S2 is again cos theta d phi up to sine. And all the sign and coefficient that I haven't put in the game are such that with this condition, the background cancels the spin connection, so that this, exactly as we did yesterday, reduced to the simplest equation, the mu epsilon equals 0. So even the black hole satisfies supersymmetry with this trick, the topological twist. There is a background for their symmetry that cancels the spin connection. So again, the background is similar to the one that I introduced the hour before. The supersymmetry is realized precisely in the same way. Why this formalism of gauge supergravity is useful? It's useful for the following reason. There is something called the attractor mechanism. It was found in for asymptotically flat black hole by Sergio, Strominger, and Kallosh 20 years ago. It's called attractor because in that case, for asymptotically flat black hole, typically asymptotically the scalar fields are unconstrained, are moduli of some Calabi-Yau compactification, but when you go near the horizon, they, independently from the original value, they assume a particular value which is fixed by the charges of the black hole. And this particular value can be found by a general trick, which is the extremization of a function. The same trick works for asymptotically flat black hole. For asymptotically flat black hole was done by Dall'Agata and Gnecchi 5 or 6 years ago, and it works in the following way. You just construct a particular function that enters, that is made with the ingredients that I mentioned before. This particular function, let me call it minus I tilde,
it will be a close relative of the partition function, of the logarithm of the partition function that I'm computing in field theory, and has this specific form. It's constructed in terms of the charges, electric and magnetic. So these are the derivative of the prepotential, and there is the denominator that depends on these gaugings. Again, most of the time, this second term is 0 in our application. So you construct this quantity, and then you extremize it. It's just you see, it's just a function of the scalar fields. There are no derivatives with respect to space-time, so you can just extremize with respect to the scalar field, get the minimum value, and it turns out that the minimum value that you find in this way, and you find it by looking at the supersymmetry equation, you evaluate the supersymmetry equation at the horizon, you discover that the values x star is the value of the scalar field at the horizon. They typically run along the solution of the black hole. And more than that, you also discover something else. You discover that the entropy of your black hole is given up to factors that in my normalization depends on the choice of metric for the Riemann surface and the Newton constant. This function here, evaluated at the value of the scalars, reproduce the entropy of the black hole. This followed by looking at the BPS equation. And it's called the attractor mechanism. So essentially to find the entropy of your black hole, you just need to know a few things about your Lagrangian. What are the charges? What is the prepotential? What are the gauging? And then you can do an algebraic computation. Taking a derivative. Let's include the derivation in the notion of algebraic. You don't need to solve differential equation. Let me tell you something else, just a subtle comment. I will not comment much about this. Actually, there is a second constraint on the charges. This comes from supersymmetry. It turns out that there is another constraint, this time highly nonlinear, so I'm not writing the explicit form. There is a particular function of the magnetic charges and electric charges that should be 0 in order for the black hole to be supersymmetric. This function in the general class of Lagrangian with vector fields has been found by, in recent years by Katmadas, and Almagi gave the most general result about this in 1415. And if you want to have a look at it, you can open this paper. You will discover that it's quite a mess. It's constructed in terms of the quartic invariant of gauge supergravity. It's mostly unreadable, okay? At least to me. I'm sure that Sergio can interpret immediately what's the meaning of that. But for us, common human beings, it's a complicated and very long expression. Instead, this one is very simple. What's the logic of this? Well, the logic of this is that when you do this extremization, you can get a result. These are complex scalars, and the result can be complex in principle. Okay? The second condition is the condition that tells you that these guys here, the result is real. Okay? It's such that the final result for the entropy of the black hole is real. Okay, let me see if you need to know something else about EDS black hole. Just a comment. And then we go to the interpretation, and tomorrow we go to the real computation. So some of these black holes are interesting to me because they can be uplifted from gauge supergravity to an M-theory background. In particular, you can have the M-theory in ADS4 times S7. When you dimensionally reduce on S7, you get a gauge supergravity. And you get a gauge supergravity with a bunch of things, because you will have vector fields, you will have infinitely many Kaluza-Klein mode, but you can essentially truncate the Lagrangian to the Cartan subalgebra of the symmetry of S7. The symmetry of S7 is SO8, so you expect, as usual in ADS-CFT, SO8 gauge field. If you truncate the effective theory to the vectors that live in the Cartan, you get a gauge supergravity. Essentially, you get a gauge supergravity with NV equal 3. The number of vectors should be always NV plus 1, so it's 4. One of the 4 guy you want, if you want, in this formalism is the guy sitting in the graviton multiplet. The other 3 are vector fields in vector multiplets. And for reference, you will see tomorrow why this is important. You go to the papers, and people did the explicit dimensional truncation. So they took the dimensional reduction from 11 dimensions to 4. They wrote the gauge supergravity that correspond to this truncation, and this will be important tomorrow. For this class of black hole, this particular function that fixes the Lagrangian of the gauge supergravity is the square root of the product of the 4 homogeneous coordinates, okay? So exactly the guy that so with this information, you put the square root here, you take derivative with respect to x, and you compute the entropy. The other data that you need is that this weird guy, the magnetic gaugings are 0, so there is no problem with those, and the electric gaugings are all equal. Okay? So there is just one constant, g, which is essentially the radius of anti-de Sitter 4. Okay? This fixes the value of the superpotential on the vacuum. So if you take this expression, you plug it there, and you do the computation, you typically will get a mess. Let me show you what kind of expression you get in the simplest case. The simplest case is no electric charge. So all the Q lambda are 0, and I take all the possible magnetic charge that I can identify to be equal. So there are 4 of them, but there was a constraint, sum over G lambda, P lambda equal minus K. So only 3 are independent. You can choose 3 of them and set them equal. So this computation, I think, is completely correct for the sphere. For the Riemann-Genus surface, you probably did a multiplicative factor, not much more, but the result in this particular case is something like that. So if you are familiar with the asymptotically flat black hole entropy story, you probably expect to find something simple. In the original Strominger-Waff example, in the original example in the 90s, the entropy was so simple as square root of the product of object, square root of Q1, Q2, Q3. Okay? Very simple function. Here, in the simplest black hole that I can write, you see that it's already a rational function of polynomials multiplied by other rational functions. I can write the split expression for 3 different charges. Will be a mess. Will be a bigger square root of polynomials. Honestly, I cannot write explicitly. Well, I can, but I need a mathematical notebook to write expression for the electrically charged black hole, because I need first to put this quartic invariant and other things. So in general, the message is that the expression that I want to derive from field theory is a mess. Okay, this is the result I should expect from my partition function. I'll show you tomorrow that I will instead match this general construction. So from field theory, you will get precisely something that you have to extremize, and you will have exactly this form in general. So in the last 5 minutes, let me just tell you the logic of the rest of this computation. So now that we have all the ingredients, we can start building up the holographic interpretation of the black holes. And the holographic interpretation of these black holes now is simple enough. So what I have a metric that asymptotically is of anti-de Sitter form with a boundary metric which is sigma g times r. I'm still working in the Lorentzian signature. At a certain point, I will Wick rotate my field theory. So if you want, you may also think that this guy is, the time is Wick rotated to a Euclidean S1. Okay? But there is no actual need of doing that for the black hole. So let's stay in the Minkowski where everything is safe from the point of view of the black hole, and we really have a black hole. This first information tells me that, okay, if I want a dual interpretation, I need to put my conformal field theory, and tomorrow it will be the conformal field theory, since this black hole will be asymptotic to ADS4 times S7, the conformal field theory will be the dual of ADS4 times S7. So in any case, since you have a asymptotically anti-de Sitter behavior, you expect the existence of a conformal field theory there. And what you are doing with such a metric is to take your conformal field theory and putting on sigma g times r, okay? Or if you take the Euclidean version, you get sigma g times S1. Precisely as yesterday. Yesterday sigma g was S2, but I told you today that you can easily generalize to a Riemann surface. The second information is that the gauge field in the bulk have a profile, and this profile is not dying at the boundary. Indeed, at the boundary, what you find, since you need to have a non-zero magnetic charge, it means at the boundary A lambda doesn't scale with R. So you have a term that for the sphere, for simplicity, let me write the case for the sphere, is just a monopole, okay? Plus correction in 1 over R, because all the fields will depend on the bulk coordinates. So this is what you have. Now you should remember a couple of basic things about holography. First thing, all gauge field in the bulk correspond to global symmetry in the boundary, okay? That's the basic principle. So all the guys that I see here are just the sources for global symmetry in the boundary. And what I'm doing here, whenever you have a field that has non-zero profile at infinity, clearly this profile should solve the equation of motion. And as you probably know, the basic ADS CFT dictionary tells you if you want to give an interpretation of these terms, you first have to decide whether this is the, there are two possible, Joanna mentioned it before, two possible solutions of the equation of motion. One is not normalizable at the boundary, the other one is normalizable. Or more naively, one is not going to zero in this particular example, and this is this one, so this is the dominant term. It's not normalizable. And whenever you have a non-normalizable deformation of the bulk background, it means that you are taking your conformal field theory and you are deforming it. In particular, in this case, you are deforming it by turning on a background, a magnetic background, for the global symmetry associated to A. So essentially, in practice, in the Lagrangian, you will certainly couple the current of the flavor symmetry to A, and you will put extra term to have a consistent supersymmetric and gauge invariant Lagrangian. So what you are doing is deforming the theory. How? In a simple way. You are putting magnetic charges for the flavor symmetries, magnetic charges P lambda for flavor symmetry. remember something, you should, is exactly what I did yesterday and I was doing at the beginning of this lecture. The topologically twisted index is precisely this object. You take the theory on sigma g times S1, you put magnetic charges for the flavor symmetries. Next, the black hole has also, now I finish, the black hole has also electric charge. If you look at electric charge, you will discover that they sit here in the term that are 1 over r. So these are subleading correction, or better, in the language of ADS-CFT, are normalizable modes. So normalizable modes, non-normalizable modes correspond to deformations. Normalizable modes correspond to states in the conformal field theory. Or better, there is some operator that is having some expectation value. Okay? So it's a different state in the conformal field theory. So essentially, the meaning of the holographic meaning of the electric charge is the following. I'm considering my conformal field theory. I'm deforming it with the magnetic charges, and then I'm looking to states in this field theory that have a specific electric charge. So this means that your black hole is a collection of states with average electric charge Q lambda. So you want essentially roughly that the vacuum expectation value of this current is Q lambda. Roughly, very roughly. So this is what you want to compute. I will stop writing a formula. So even without the previous lecture, since the black hole is supersymmetric and I need a supersymmetric object that should describe this particular situation, I would be writing something like that. I would like to compute some sort of partition function for all the modes in this background of magnetic charges, external magnetic charges. And if I want to study states which have a particular electric charge, well, I can do as in statistical mechanics. So I introduce a set of chemical potential in my partition function, and I write this object, which will be a function of what? Of all parameters in the Hamiltonian, and the Hamiltonian depends on these magnetic charges. So you are deforming your theory, so this will be a function of all the magnetic charges, and it will be a function not of the electric charges, but of, sorry, I should probably put index in this way, but it will be a function of a dual chemical potential, like in statistical mechanics, with the idea that essentially, roughly, and tomorrow I will be more precise, the derivative of the partition function with respect to the chemical potential is the vacuum expectation value of the electric charges, which is the electric, with some normalization, should be the electric charge of the black hole. So if I were able to compute this object, I could try to answer the question of what is the entropy of the black hole. This is a statistical mechanical model. I have a partition function. From a partition function, I can compute an entropy. I'll tell you why tomorrow. And luckily enough, this guy is precisely the topologically twisted partition function. Tomorrow, I will give you the detail. So the object that I defined yesterday can be used to enumerate the states of a generic dionic black hole in this setup. I'll tell you the details tomorrow, and I'll also show you how to compute in the case of ADS4 times S7. Okay, I stop it here.
Any questions? Yes? Could you please explain shortly about attractor mechanism that you mentioned?
What you want to know?
Attractor mechanism.
Attractor mechanism. You want to know more? maybe we can do for in the discussion section. This is
in your topic.
No, let's postpone these details to the discussion session. Okay, so we go now to the last lecture of the hour.